Hello, everyone, and welcome to the first official IT seminar series. This is one of many to come this year, and it's my great honor to welcome our three great speakers here today. The seminar topic today is on paved roads and safety, and I'm going to go ahead and share my screen. Perfect. So our first speaker today is Dr. Sina Varamini. He has a PhD degree in civil engineering from the University of Waterloo. He's a sessional lecturer at York University since 2019. He's also an adjunct professor at the University of Waterloo, Manitoba, and New Brunswick. He is research and developer manager at ASPHALT Industries Limited. And he's also a member of the Canadian Technical Asphalt Association, Transportation Research Board, Transportation Association of Canada, and American Society for Testing and Materials. So welcome, Dr. Sina Varamini.
Perfect. Okay, great. Well, hello, everyone. Thanks for tuning in. And today I would like to present the past, present, and future of the Canadian roadway infrastructure and try to be really on a high level and look at the design and construction perspectives. So for what I prepared really for today, it's a 15-minute talk, and I just wanted to be as brief as possible, but more detailed information on what's coming up in future. So this slide is really capturing what's happening in terms of roadway history. You can see the past, the roadway that is not really doing any functional, basically it's not functioning as it's intended to. And we're looking at the present, really heavily loaded traffic applying on the roadway infrastructure. And then we are looking into the future that hopefully by the end of this presentation, we have an idea of what's happening or what's coming to us in the future. Now, before I start, what is really the pavement structure for those who might not be necessarily familiar with the pavement structures? They are layered structures and they are placed on ground. And then they're composed of layers to provide three primary functions. They are distributing the load to the subgrade, and then the subgrade in this case would be the foundation for roadways. And it has to be an acceptable level of stress. Very similar to structures in terms of the building structures or bridges or any other structures placed on subgrade soil. And at the end of the day, it has to provide a safe, a smooth, and a quiet, comfortable ride to the users. And by doing so, we want to make sure that it is layered in a way that it has a waterproofing characteristics, and it does provide a level of protection to the underlying layers. And that is basically getting translated into providing support to the structure when we have events of rain and snow, and then really doesn't allow the structure to be saturated, and then which could lead to the loss of support. If you look at the historical design and construction trends, we can see these three primary functions built kind of in mind right from the beginnings, when the Romans had the roads throughout the trading networks. And you can see the structures are fairly thick, and that was mainly due to the construction techniques and lack of ability to produce materials in more precise and more finer particle sizes. And then as we go throughout the history, you can see how the pavement structure has been really optimized to be as thin as possible, to be cost effective, and allow us to expand the network throughout more areas that they need to be paved. We get to McAdam and the early 1900s that really the pavements are looking at more technology advanced construction techniques, as well as the production of materials. We get to today's pavement structures that they are composed of two main structures mainly. They refer to as flexible and rigid, and we'll know within the next few slides why these two terms are being used for these type of pavement structures. And we have the composite, which is the hybrid of the two, flexible and rigid. And when we're looking at the flexible pavement, we do have the asphalt cement bound materials acting as waterproofing and providing that a smooth and safe ride. They are placed on top of the granule materials to provide drainage and basically ensuring that if this structure gets saturated at some point, it would not be detrimental to the adequacy of the structure. So it does allow for the water to drain out. And then we have the subgrade, which is the engineered basic foundation for the on-ground structure. Then we're looking at the rigid point of view, and then we are having the concrete bound or the Portland cement bound material as a surface layer in lieu of the asphalt thick materials, and that they are placed on top of the granule materials for the same purpose as the flexible pavement. And then subgrade in the two structures are shared, and then basically it's a foundation for the layers to be built upon. And the composite is the hybrid of the two. These are the two roads that you predominantly see across the Canadian road network. They are referred to as basically the white top, which is the right, and the black top, which is the flexible and asphaltic materials. The two pavement structures that have different cost cycle, and they have the different behavior, and that is mainly due to the material used on top of the granule materials. We have the asphalt bound materials that they are flexible, and then they are coming from the crude. And we have the concrete materials that are made out of the Portland cement, the same material that we use for building bridges and structures. And the difference between the two really translate into difference between the stress distribution throughout the pavement layers. And as you can see, the red line is really showing the stress distribution down to the subgrade. And as you can see, the flexible is allowing for more of the stress to get disseminated down to the subgrade level, as the rigid pavement, due to its rigidity, is taking more of the stress and it's not allowing for that stress to get translated to the subgrade in that level that flexible does. Now, in terms of the flexible pavement, the band materials are composed of 94 to 96% aggregate. The aggregate is manufactured, or it could be natural, it could be recycled, but essentially gets crushed into different sizes and then it basically mixed with a binder material. The binding agent in this case is an asphalt binder. It is a petroleum byproduct. It could be modified, it could be conventionally used as it comes from the refinery. And since it is a material that it needs to be heated up, and it needs to be heated up to a level that is fluid enough to cover the aggregate particles, we need energy that goes into the production of this material. And that energy is coming from the heating up the asphalt binder, at the same time heating the aggregate to be able to mix the two together. And you can see the portion of the mass that goes into the bound materials, as well as the cost relatively for each of these components. As I mentioned, the asphalt cement binder is petroleum-based byproduct. Essentially, when the crude gets sent out to refineries, all the different distillates gets collected through a distillation tower, as you can see on the screen, and each tray is collecting the commodities that get sold out into different markets. We have the naphthanes and the kerosenes and the gasolines that they have different market. But at the end of the day, the byproduct and the material that is the residue of this tower is called an asphalt cement or asphalt binder. And that material gets distributed throughout different markets, which paving or production of the asphalt bound materials for roadway infrastructure is one of the biggest or the major market segment. Because of the chemistry and because of the relativeness of the asphalt cement to the chemistry of the crude, this material behaves differently, and it has a temperature and time sensitivity over the course of the in-service life of a pavement. And it is because of that sensitivity that you will see the stress distribution as shown on this slide. A flexible type that the top portion, which is asphalt thick material, is flexing, and basically as the stress gets distributed down, is getting less and less down to the subgrade. In contrast to asphalt thick materials, we have the concrete surface layers. We have composition of 8% air, and we have 7 to 15% of the Portland cement. and then you have water and aggregate. So very typical to what a concrete would look like, and then it is because of the Portland cement that a level of rigidity gets added to the bound material, and that rigidity gets translated into the way that the stress of the traffic is distributed down to the subgrade. Now, when we're looking at the whole market, all these two types or the composite types not only used for the roadways. We can see it gets used in mining applications. We use it on bridges. We use it on urban roads. We even use it for seaports. As a matter of fact, you might already have a version of this roadway on your driveway. It basically, we use it as a driveway for houses and even commercial driveways, or pathways for bicycles. And then the bus lanes, as you can see, they come in different shapes of a color. When we're looking at these materials, it is really important for us to understand what does influence the deterioration of this roadway. And this is an understanding that it's been gathered for last 60, 70, 80 years. It is a historical information that it's empirical to us, and we gained that throughout the time. And then really what we understood is the pavement structures, since they are exposed to climate, the environment that they are placed in is playing a major factor on the deterioration of the roadway. The deterioration here is shown as a measure of serviceability. It could be a smoothness is deteriorating. It could be the structural adequacy is deteriorating, or it might be as just simple as the rate of pothole basically being shown on the surface. But environment, then traffic going hand in hand, and then we have the structure itself in terms of the thickness and then how resilient the material is, and what material we really choose for the roadway to become an important factor. Construction maintenance are the two others that, again, they play major role in the way that the pavement is placed, the way that the pavement is in place, and the way that it really deteriorates over time. We design pavements for 20 to 50 years. So it is really important for us to not only understand these factors, but understand how these factors change over time. And after understanding the factors influence on the pavement deterioration, it's also important to know how the pavements are playing a role in the circular economy. That is looking at the way that we design it, the way that we construct it, and the way that we use it over the in-service life, and how all these three go hand to hand with preserving the infrastructure, maintaining the infrastructure, and when it comes to the end life, how the material is getting back into the cycle that enables us to use that 100% of the material either in place or have it taken out from the location of the road and use it in different locations. As I mentioned, the factors that they influence the pavement deterioration are not only important at the time of the design. We want to know how the climate is changing, which is one of the major topics these days, the rapid change of climate. We want to understand the traffic, which is the primary point of the stress. That stress is being put on roadways, and as the traffic is changing, the stress is changing. So when we are designing, we have to look into a level of factor of safety to be included into the design, but we don't want to over-design, because then the cost would be basically increased and might not enable us to place the pavement. And then the change in crudes, changing refining practice. Crude is not an unlimited source. It could change, deplete it anytime soon, or basically what we have to do is find alternatives to crude or even Portland cement if we need to, and then go out of the unconventional materials to be used for designing and constructing roadways. So what does really look like for future of Canadian roads? And this is something that I have in mind, and we're working closely with a lot of universities and then including the National Research Council to really understand the materials. Understanding the materials under accelerated loading facilities. These are the facilities that they torture test the material in really shorter period of time. We're looking at months, or it could be years. But what we're trying to do is understand what would happen to the roadway materials in 20, 50 years under a short period of time. And that's why we call them ALFs, or the performance testing, to be included. And that gives us the ability to understand materials, artificial intelligence, and then really look into how that material could be put into different designs and different geometries of the structure. Then what we do is we look at the pavement instrumentation. These are instruments that they get placed throughout the layers of pavement, and really enables us to understand the stress and understand the resultant strain, or understand how much of a pressure is being disseminated down to the subgrade level, and really allow us to gauge ourselves with the baseline of the pavement adequacy when it was established at the time of construction, and then help us gauge the deterioration rate for the pavement when it comes to future in-place performance. Also, what we're working on is looking at the automated vehicles and then how they connect within each other, and how that aggregated data can be used to really understand how the roads are performing. If one vehicle is capturing a pothole in one location, and then the other vehicle is capturing a pothole in a different location, that data can be aggregated and sent out to the road authorities and help them understand how the roads are overall deteriorating within their network. And that will help them allocate budgets and what they need for repairs, and be really approaching this in terms of the proactively or passively in terms of maintenance and rehabilitation. So that goes into the field artificial intelligence that it's been worked on right now. And all those information, again, aggregated, it goes into understanding of the pavement deterioration, how the pavement deteriorates, and then at what level of pavement condition index we have these roads at, and then what do we have to do in terms of the budget allocation for preservation or rehabilitation of these roads in 5 years, 10 years, and 15 years. It's really looking at in a smart way of allocating budget and being proactive when it comes to the maintenance and rehabilitation strategies. There are other types of the future or futuristic roadways been coming into the picture. Those are the roads that we're working on in terms of harvesting energy as much as they can, and make them really self-sufficient when it comes to managing the network for the posted speed, or in terms of cameras, or in terms of any energy that needs to be put back into the place. That goes back to the circular economy, making sure that the roadway, if it needs energy, it harvests it itself. You can see some layers of interactive instruments are being placed within the pavement layers to allow us for harvesting the energy as much as we can. And on top of that, I gave you the glimpse of what's coming up in 10 for 20 years, but really in terms of the knowledge we are advancing, but we're losing a workforce. And then that's something else that needs to be considered. We are losing the workforce because a lot of energy for universities are being put in place into different industries, for example, robotic or computer science. And then when it comes to the civil that is related to pavement structures, we're lacking labor, we're lacking expertise. And if the universities do not invest in this market segment, we'll have more difficulties achieving the futuristic goals that we have for the roadways. So I just wanted to bring this up and say everything is not great. We still have to overwork. And with that, again, remember, all we have to do is use what it works for us, eliminate what it doesn't, and we have to be as simple as possible. And that's something I got from our friend Albert Einstein. With that, I would be more than happy to answer any questions you may have.